So basically we are going to talk about seismic analysis. Let me just summarize this for you and then we can go on further on this slide. What is the difference between each type of analysis and what information is provided by each step. So let's start with equipment static analysis. This is based on the assumption that the building only has one mode and only one mode is important. So this is based on first mode response, equivalent static analysis, and the load, the force distribution and everything is based on the first mode response. That means it is assumed that there is only one mode of the building contributing to all of the base shear or all of the response from the earthquake, and the higher modes are not contributing anything. That is, and so based on that assumption, single degree of freedom structure is created, and based on that, this analysis can be simplified because it's only using one mode. Okay. Come to response spectrum analysis. Response spectrum analysis has the ability to use many modes because you can carry out the response spectrum for one mode and second mode and third mode and fourth mode and add them together. But the only missing point is that the maximum point from the ground motion is taken for each vibration, each time history. Only one response point is taken, right? So it can respond to many modes, but the ground motion, only the maximum response is considered. That is why we call it spectrum, that means the boundary of the response, maximum and minimum. So it has no sign, it is an absolute maximum value. I will show you later where it comes from, right? So response spectrum analysis goes one more step, that it considers many modes, not just one mode, but only the maximum response from the actual ground motion. Time history analysis considers the response for every time step and includes all modes. What is important about history? The assumption about history is that the present event is affected by the past history. That is why we are talking about the history. So that means what we are saying is that if the structure is here and the ground motion starts from this one, after the first second, if the building deforms here and the second wave comes, then the next response will be calculated from the deformed location of the structure, not the original location of the structure. So the previous deformation, which has already happened, will be used to calculate the response at each time for the exploration at that point. So the entire history of deformation since the Earth's beginning of the calculation is maintained. That is why it's called response history analysis or time history analysis. The correct word is response history analysis, not time history analysis. Compared to response spectrum analysis, same way it should be called response history analysis, not response spectrum analysis. Response spectrum means you are taking the maximum value of the entire history. Response history is you are taking every point along the time step, maintaining the previous history. And that is what is very interesting, because if the structure has already deformed here and then the next wave comes, exploration, it will deform further from here. So that means the response will be accumulated, and if the structure is going this way and the ground is trying to push this way, then it will be an interaction between, and the structure may deform in very, very complicated higher mode responses, because then it simply, if it is only moving this way, first mode will be predominant. But if it is moving this way and you move the ground this way, then it will bend over, right, in a complicated response, activating higher modes, right? So that is why the time history or the response history takes care of all the modes, including the previous history of the response. Now, what is non-linear time history? What is the difference between linear time history and non-linear time history? Linear time history is assuming that at all times the stiffness of the structure is the same, irrespective of the deformation state or irrespective of the time. But non-linear time history is saying that not only is the history of deformation important, but the changes in stiffness are also important. So if the structure has already, so if you go to this way, so that means if the structure in the first deformation happened and at that time there was some cracking, that cracking will change the stiffness at all locations, so the stiffness will be modified at any. So the next ground acceleration will be applied to modify stiffness, not the original stiffness. So at every point the structure is moving, the stiffness is being modified, and the next step is using the modified stiffness. So two steps are being considered: changing properties of stiffness and changing force direction and magnitude, or displacement direction and magnitude. This highly complicates the things, because when you push something, every time it becomes nonlinear, you have to trace the nonlinear path, converge, and move to the next time step. So that means within each time step, you have to do a nonlinear conversion before we move to the next one. So if there are 4,000 time steps, each time step has maybe 10 iterations for nonlinearity. We do 40,000 analysis. So for a typical ground motion, you run the structure analysis 40,000 times rather than running one time. So the effort is so much more. And the changes in stiffness can be done in these portions. And some programs handle some and some don't handle some. Material changes, properties in material change, property changes in cross-section properties, changes in member stiffness, and changes in structure stiffness. And this is something very, very important to remember, that not all analysis can be done with all changes. Sometimes we combine the stiffness and material nonlinearity into one nonlinearity called hinge properties. Right? You combine them together into moment curvature curve, which is a combination of material nonlinearity and section nonlinearity. And then add on top of that the P delta effects, right? And the buckling effects here. And then on top of that, we add the effects of large displacement, in which we assume that the structure is not the one that we started. Now you might say, what is large? Do you know the difference between large displacement and small displacements, right? Small displacement means that if you started with a structure like this, even if it is deflecting a lot, the structure is still assumed to be a beam with a hinge in the middle. So it will not give you axial forces in the members, even if it deforms too much. It will always assume that it is still a beam because you started with a beam element. Large displacement analysis is that when it deforms, it will change and it will find out that I'm not a beam anymore. I am actually two members with truss configuration, and I need to now carry the force by axial direction. Beam has no axial properties. Normally it will carry forces by bending only. So it will try to carry the forces by bending because it thinks I'm a beam. It's a small displacement. That means the deformations in the structure do not change the geometry of the structure. The original geometry is assumed. In a large displacement analysis, the change in the geometry changes the structure, which is very different from simply changing the cross-sectional properties. So when you do the analysis, nonlinear analysis, you have the option to do a small displacement analysis or a large displacement analysis. Right? SAP and ETAP and these programs have the capability to do large displacement analysis also, which means the structure's deformation, if this deformation of the structure is used as the new structure, deformed structure is used, right? So we can include structural nonlinearity, member nonlinearity, section nonlinearity, material nonlinearity into that nonlinear analysis, and that obviously complicates this analysis quite a bit. So this is full nonlinear dynamic response history analysis, which has the capability to do everything that we need. Alright? So now you can see easily that you can go from a simple static analysis code based on just first mode. You can go to response spectrum analysis based on a specified number of modes, but only the maximum of each ground motion response, or you can do a linear time history in which the entire deformation history is remembered, but the section properties and stiffness are not changed, or you can do a full nonlinear response history analysis in which the structure is also changed every time a deformation happens, and that deformed shape, new stiffness, new structure is used for the next step of iteration. So are you now clear about all these analysis methods? No confusion. And this one, of course, is without any loading, without any damping. This is the natural, and this is the basis for everything else. This determines how structure two different structures will respond. This is, you must see this one. This is a structure with 0% damping. That means if you move it in this way, it will continue to oscillate with the same amplitude, with the same frequency forever. It will never stop. Like you go to a shopping center and they have those pendulum click, 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 never stops, right? Or the clock, that one never stops. Damping is 0, right? If I say that structure after some cycles, the frequency will remain the same, but amplitude will drop, and after some time it will stop, right? That means it has some damping, and this is the effect of the damping. So these number of cycles approximately represent the damping. So if we say that a structure with, of course with 0 damping it will go forever, right? But let's say 100 is approximately the number of cycles for a 0 damping definition, approximately, right? Then 5% damping means that it will stop after 20 cycles, right? 100 divided by 5, about 20 cycles, it will stop approximately. And when we say 2%, it will take 50 cycles before it stops. When we say 100% damping, it means it will stop after 1 cycle, right? So this is a ratio between damping, is a damping of the structure divided by the critical damping of the same structure. Critical damping is defined as the damping which takes 1 cycle to stop. That is called critical damping. That means 100% damping. That is called critical damping. So this is the ratio between critical damping and actual damping. And this determines how long the structure will vibrate before it will stop. Now are you clear? So a concrete structure has more damping, or a steel structure has more damping? Sorry? Concrete structure. So which one will take longer to stop, concrete or steel? Steel. Right. So these kind of things you have to remember. It's more flexible, as you can see, it will continue for longer things. Right? So damping is an indication of how much energy things absorb and how quickly they can come to a stop. Right? So if they absorb all the energy, they have no more energy left to oscillate. Clear? Okay, so that's what it is. And another thing, of course, you know multi-degree freedom, that this location, at each location, force is a multiple of the mass and acceleration at that point. And this leads to the modal shapes. This is called a mode shape. Right? This is the first mode shape. How the mass is displaced in a particular configuration vibrating at a certain frequency. Okay. So we talked about last time a little bit about this slide, that if the structure is stiff, it will generate more force. If the structure is flexible, it will generate less force, which means we are in control of how much force is generated in the structure, not earthquake, right? So I gave you the example of the structure with base isolators, right? I think I have some videos today to show you probably. Yeah, you'll see some videos, maybe last day. Let's keep the videos for Friday. Yeah, some interest for you. Um, Base isolators means that you completely separate the structure, so ground will shake, structure will not move at all, no force will be generated. But basically, to the cyclic load, many things can happen. Many ways the structure may respond. For cyclic load, a structure which is perfectly elastic will continue to respond elastically back and forth, and the line will not go like this, it will just go like this, up and down, go up same, come down same, and so on. But normally the structures have non-linearity, so they go this way. When you arrive here, they unload and go this way and come this way, and then you load here, they start from the last position, and every time the next cycle will be like this, cycle will be like this, right? So every time when you load and unload, the structure takes a new path, or the section takes a new path. And that changing path is an indication of the member or structure's, what should I say, ability to withstand cyclic loading, right? It is an indication of stiffness, it is an indication of strength, it is an indication of energy absorption, it is an indication of its integrity, you may call it, durability, you may call it many ways. Basically, the ability of a member to withstand cyclic loading without breaking much is the response that we are looking for. And the area of this diagram represents the amount of energy absorbed by the structure or member or material. So we can draw these kind of hysteresis loops at every level, material level, cross-section level, member level, structure level, right? Same thing, we can keep on doing that. This is a very interesting diagram. And this is very interesting because it goes contrary to normal thinking. And it is an interesting thing, especially related to Bangkok. Normally people feel or people say that tall buildings are very dangerous for earthquakes. Actually, may not be the case. Actually, it may be the smaller buildings which are more critical. In fact, the amount of base shear generated by earthquake for a small building, two-story house, could be as much as 80% of the gravity load, or 60%, or 90% even, or even more than the gravity load is possible, right? However, for a tall building, typically these drop down to 10%, 15%, 12%, 20% at the most. So, as a percentage of the gravity load, even though the tall building have another problem because they're tall, other issues, but the amount of force acting per weight of the building is actually larger for smaller buildings because of the nature of response spectrum, nature of the response, and the effect of the natural period with everything. We will talk a little bit more about that. So this is very important. This diagram, this is related to response spectrum. Because response spectrum and this building height is related to natural period. Natural period is related to response spectrum. Response spectrum is related to the force generated on the structure. So that means the natural periods of the building are an indication of how much force will be generated for a particular location. For example, 3 to 5 story building here, this one here, and this. So there are many, and I don't want to go into details. It's not supposed to be my subject for now, but we will talk about it. Now, what is critical is this issue in earthquake: irregularity, right? Both vertical and in terms of the structural designing or structural engineering point of view, how can we reduce the forces on structures from earthquake? Because as I told you, the earthquake force is generated by the structure itself. So the structure is the culprit. So if you want to reduce the force, you must talk to the structure. Don't blame the earthquake. Blame the structure, right? So your structure can be designed, can be configured, can be planned in such a way that it minimizes the seismic forces and seismic response. And one of the key component of that is avoiding irregularities. because irregularities create concentration and they create dynamic weak points, right? Because things, when they start to move, they want to basically move freely. As soon as you stop them from moving freely, they generate forces. It's as simple as that. So if the structure wants to move, the ground wants to move, if you let the ground move freely, it will not create any force. If you put a building on it and tie it to the ground, forces will be generated. Similarly, if you put one tower here and another tower here, they want to move freely. If you connect them together, forces will be generated between them. So basically, all parts of the structure would like to move freely. If you can make them move together without creating internal forces, that means you can minimize the force or stresses in the structure. For example, this structure is very nice because all the columns have the same stiffness, same grid spacing. So because of the mass and stiffness is evenly distributed, they will all move together. So even if there are many bays, they don't create any friction between them or any problem between them because they all can move together because their dynamic properties are identical. Dynamic properties are two, mass and stiffness. So if the mass and stiffness are identical, things move together because that is the only one controlling their motion. You remember free vibration equation? Mass and stiffness. So if the mass and stiffness are identical, response is identical. That's the key. Here is no. Now if you connect these two buildings together, the stiffness and mass of these two buildings is not equal. They will try to move in a different directions at different times in different amount, creating forces between this location, causing it to have concentration, right? So this is called irregularity. This one also we call it irregularity. This building has different stiffness in this direction and this has different stiffness, so they will not move well, right? So this building is too long. This may have a problem. This may also have. So some buildings too long, too short, too something are not good, right? Basically, ideally speaking, a nice box building is very good. So all of these things are bad. As soon as you go here and the tower starts here at the podium, you get this whole problem between interaction between podium and tower. Biggest problem in tall building design these days is when the tower starts at the podium level, and what happens at that level is terrible actually. The force transfer between this portion and this portion is a very complicated and troublesome thing. Because suddenly the tower is coming, which is trying to move, and the podium comes, which is not moving as much, and now, so there is a lot of force generated at that location, which is not the foundation. Foundation is somewhere there. So this creates, this one or two floors create a lot of forces between the podium and the tower, called the diaphragm design, diaphragm forces, and very critical. And many people have been missing them for a long time, not designing the structure for diaphragm forces. If your building is like this, don't use simplified methods. The code specified simplified methods do not apply when your building has discontinuities. That is what we are saying. Because after all, we are engineers, we are scientists. We should be able to solve a problem, correct? We cannot just say, don't give me a problem which is complicated. The only thing we are saying is that if the building is like this, we have to do more. We have to go to higher level of analysis than the one. So here the order is like this. You know, the lowest one is code-based equivalent static. Next one is response spectrum. Next one is pushover. Next one is linear time history analysis. The top is a non-linear time history analysis. Right. So when the structure starts to become complicated, and when the earthquake risk starts to become higher, we need to go up the ladder, choosing more and more sophisticated methods. That is the whole idea. And the code, the new code, says exactly the same. We say if your structure is category this one, design category is this one, you cannot use this method anymore. Previously, it was not like that. They just said you can use it everywhere. But now it's a very important concept of design category. Design category is a combination of the structure type and the seismic risk. So they combine together to give you a design category A, B, C, D, E, F. And for each design category, there is a certain method of analysis which is specified. Right? So when the design category becomes D or E or higher, then you need to use more sophisticated methods. So there's a matrix between design category and type of analysis to be done. And all of these buildings will be categorized, if it is an earthquake zone like Philippines, all of these will be categorized as category D or F or E. High also comes in the soil in there. Right? Bad soil, category comes higher. So soil, building, earthquake combined together define the design category. And then that determines what analysis we should be following. This talks about another interesting thing which is also related to the natural period. Different ways things move, and they try to connect. It's a very interesting book. It is very like a children's book. Tries to explain what everything is. So you get a look at that book, and it shows you how the mass, if the mass is eccentric, how the building will start to twist. So twisting modes will come up, and how if you have multi-levels, then the higher modes will come up. So it tries to explain everything by using very simple analogies. So it relates that to the twisting modes of the building, and this is something that we almost always try to avoid twisting modes, torsional modes. Why? So the discontinuities create torsional modes. Primarily, the discontinuities lead to torsional modes. Torsional modes is something that we try to avoid. Why? It's about, okay, look at this building. This is a good example. If the board is twisting, that means this wall or this column on the corner is moving much more than the rest of the building. That means it is supposed to now absorb more deformation. It must have the more deformation capability. If not, it will simply break. So that means the deformation in various parts of the building is not proportionate anymore. It depends on how far they are from the point of rotation. And if they are far, they get more deformation demand or more force. They will have to resist to stay there. So which means that then they will break first. So if all the columns have the same strength, the column will break first. Even though all the other columns are still standing, the column is already gone. And that means it's not good, because just one column will become weak amongst 100 columns. But if there is no torsion, all columns will share the force equally and will not have any problem. But here, if you want to twist torsion, you have to strengthen some columns way more than the others, right? And that may not solve the problem all the time. So torsion is bad because it creates unequal demands on the structural members of the same type based on their distance from the rotation center, and that creates a possibility of failure. So the possibility of failure of some member becomes higher than other members, even though they have the same design and same, otherwise vertical loading is the same, but one column becomes weaker than the other because of the torsion. And that is not good, because then that means you are creating, you design the structure very well, and just because of one column, it fails, right? And if you try to strengthen every column to that level, it's totally unnecessary. It's a lot of cost, right? So the best is to avoid torsion, if you can. And we spend a lot of time in our structural system development to eliminate the torsional modes in the beginning, especially in the first three modes, the first two modes. Third mode can always be a torsion, right? In fact, third is typically a torsion, but we don't want the first and the second mode to be torsion, if we can avoid it. If it is a torsion, then the category of the structure becomes higher. Then you need to use more sophisticated analysis to capture the dynamic redistribution of the forces. So this is all about that. You can see. Another interesting thing is pounding, which we need to consider. Pounding is when the two structures are very close, and when they move, they can hit each other. Because what happens is, originally people have been thinking that expansion joints are very good. So when the building is unsymmetrical, they put expansion joint between them. But an expansion joint is typically 25 millimeter or 1 inch wide. They do not think about the structures moving and hitting each other. So a seismic gap and expansion joint are two different things. Unless you provide a seismic gap here, these buildings will have a chance to collide with each other. So that means this building may move this way, this building may move this way, and they may actually hit each other. And if they hit, of course, they will be damaged. Now, what do you think? Let's see your guess. What do you think if your building is each 30-story tall, right? 100 meters, let's say each building is 100 meters tall, and they are very close together. How much gap should be given between them to avoid ponding? 0.1%, 0.5%, then you are right, because 0.5% means 50 centimeter for each building, total is 1 meter. But 0.5% deflection is based on not the non-linearity and not for the actual forces. This is based on the design forces or design earthquake requirement, typically for wind. Earthquake, drift, or earthquake can be as high as 2% or up to 3%. For highest earthquake possible, it can be, and if the structure is well designed in terms of the ductility, it can go as high as 3%. So normally we design this for at least 2% minimal drift. That means 2 meter each building, 4 meter gap, as big as this room. So people, if they think that they provide a small expansion joint of 50 centimeter or 50 millimeter or something, obviously it is not going to work, and the buildings are going to hit each other. So the seismic gap can be quite large, and if you do not do that, the ponding can happen in buildings. So ponding, and then the problem is ponding and torsion. So if the building twists also, and if the building is very long, then that twisting can actually cause more sway than simple sway, because you can imagine the building, this one twisting, this portion will sway much more than your average. So if the two buildings are long and they are twisting, then their torsional mode will hit corners, right? So that's why torsional mode is also important when pounding effects are investigated. You can see from this one, this is in Pakistan, I think, right? Yeah, Islamabad. So there were many towers. This is one of those examples which is very, very unique and very, from the structural engineering point of view, interesting but very tragic. There were 6 or 7 towers of identical nature, same design, same contractor, same everything, and just one of the towers collapsed completely, all others not damaged. And it was a big question, why did this happen? Because of the nature of the location and the way that particular tower was aligned in direction of the seismic. So the forces of that tower, even though it's the same design, were much higher than the other towers. Right? It's very sad, but that's what can happen in this building. Another one, as you know, this is also very sad earthquake. 80,000 people were killed completely, and you can see all these buildings are small, 2-story. So it's not the tall buildings necessarily. So it depends on the damage. It can happen anywhere, and damage can be. So you have seen most of these pictures. I'm sure Dr. Kanai has shown you. All of these are problems. Heavy mass on light structures, then you get this problem. This kind of effect. Large stiffness, flexible. So you have seen probably these are not things that you should do in a structure. If you do, you must design for them. there's supposed to be a story here which is gone now. It's completely gone. There was a floor here. So only the lower floor disappeared. Everything is fine. The lower floor just disappeared because of the weakness in columns at that floor. We talked about various analysis procedures, methods for seismic analysis, and we talked about why they are needed, because the simple methods cannot capture the difficulties of complicated structures and high category structures. But if you do a nonlinear response history analysis with everything properly done, you should be able to capture most of these issues and specific demands on particular members. So we have the equipment static, we have the nonlinear static procedure or pushover method. Pushover method has many sub-methods in there, I think 24 to the last count. So there are 24 types of pushover methods. There was a time when everybody was writing a thesis on pushover because it was such a useful thing that everybody wanted to do some research. Linear dynamic procedures and then nonlinear. So you can have this category. You know about the soft soils, or the effect of that. There are some other analysis also that you may need to do. Response to harmonic forces. Response to periodic loading. Periodic loading is not the same as seismic. Periodic loading is like a machinery sitting on your floor, vibrating machinery. It's rotating, and every time it rotates, it puts a force on the structure. So vibrating machinery is a periodic loading, which also sometimes needs to be investigated. So it's a different way to do that. And then ambient vibration response and direct dynamic and so on and so forth. Do you know what do the doctors, old doctors, medical doctors, not PhD doctors, they're not even doctors, So when you go to the hospital, if you say your name and your doctor, they start to, they get confused. So normally when you go to the hospital, never say that you are, your name as a doctor and there. The medical doctors or the real doctors, what is their most important way to diagnose human health? Not the now, the older, little bit older doctor, the few years back. Pulse, right? Exactly, pulse. So a good doctor, an experienced doctor, an intelligent doctor will just look at the pulse. He will not say go and do 40 tests and come back to me tomorrow. And none of the tests will give him any result because he doesn't know what to look for, right? But a good doctor will just look at the pulse for a few seconds and he will know, or she will know, what's right or wrong. Same is the case with structures. The modal response is the pulse of the structure. So if you know how to read the pulse of a structure and the engineer is good, he doesn't need or she doesn't need much information. That's it. You just need to read the pulse of the structure and hear what the structure is telling you, and you will know the structure is healthy, not healthy, it's going to live longer, not live longer, and so on. In fact, the whole structural health monitoring is based on measuring the pulse of the structure over a period of time, right? So they install the instrument, so it will always measure the natural vibration, and that is the pulse, and based on that we can tell everything about the structure. So free vibration is the key, or modal analysis is the key to understanding the response of the structure, of the whole structure. The structure's heartbeat is only based on two items, mass and stiffness, right? And if the mass is not changing over time, or mass is not changing so much, then primary indicator is stiffness, right? So stiffness, as you know, is built from material stiffness, member stiffness, structure stiffness, cross-section stiffness, is the whole thing. So that means the heartbeat of the structure becomes a measure of the stiffness. And we also know structure stiffness is non-linear. So if the stiffness has changed over time, the natural period will change. So if we make the structure today, new structure, different natural period. After a few years, natural period of the structure will change with aging. And it includes non-linearity, includes everything. It also affects damping, right? Indirectly. So if we can do the modal analysis and look at the heartbeat, right, then we can know a lot. First of all, we can know whether the structure is too stiff or too flexible, whether it is changed over time or not, right? How much earthquake force it will attract, what type of earthquake will be dangerous to this one, right? What level of earthquake, what story, where it will be effective, everything, almost everything that you need to know about the structure response, we can tell by looking at the modal response, which means natural period and mode shapes, right? So natural period, for example, is a measure of the structure's stiffness and flexibility, or its ability to attract forces, both wind and earthquake, not only earthquake, wind also, right? It is an indication whether we need damping or not. It's an indication of many things, right? It is an indication whether the structure will interact with the loading and cause resonance or not. What is resonance, by the way? What is the most common, most simple example of resonance? Children, when they are swinging on a swing, you push somebody, they push a little bit. And when they are coming here and they're going, you push a little bit, they go further higher. When they're going next time, while they're moving, you push again. So that means your force application is matching with the natural period of the swing. So every time with the same little bit force, you can increase the amplitude so much that the person can go over. Right? So you can actually go very large amplitude, same force, if you apply it in a resonance manner. So the amplitude can increase by 10 times if the force and the natural period match. That's why when the armies, as you know, armies crossing a bridge, they say break your step, because your step might match with the natural period of the bridge and break it, right? You know about the singers who can break the glass, right? Many people try that, somebody just hit the glass. And so that is all related to natural period, vibration and oscillation. So natural period can also tell us whether it's going to be oscillation or not. Wind response, low velocity wind response can result with the oscillation. Very slow wind is moving, very slow wind, but the gust is producing crosswind response very slow. But the structure also has the same period. Then that very slow wind can create the structure to oscillate and cause fatigue, right? Things like that. So that means first thing is check for the natural period, right? Structures range, we are saying that 10-story building should have a natural period of about 1 second. If the natural period you find in the model is 3 seconds, what should you do? Simple question. You didn't say that maybe you're wrong, your model is wrong, maybe you put the most likely you made the model incorrectly, most likely your E value is not correct, most likely your stiffness modeling is not correct, most likely your mass is not correct. 90% of chances are that you made a mistake. You better check first, right? And that means this is one of the ways to check your model. If the natural period comes out to be very strange, something must be wrong with your model. Check that first. Most common mistakes are wrong unit for E value, because it's easy to make an error between megapascal and some other units. Instead of 2 raised to power 10, you can make it 2 raised to power 9, right? You missed between tons and kilonewton or something like that. So most common mistake is E. When you change the E by 10 times, your stiffness changes, your natural period will change. Or you input the wrong density of the material. Instead of inputting concrete, by mistake you specified steel density for the whole, and this is not a joke. There was a building in Philippines, not your company for sure, somebody else. They called me and they said, you know, my foundation is too heavy and I cannot design it. It's just And it's impossible, your PDF program is not good. I said, okay, please send me the model, let me take a look at that. And when I looked at the model, I found that all columns, which are very big, the density assigned is steel. Obviously, everything the program is calculating based on the steel weight, which is like 10 times more than concrete weight. So every foundation, everything is 10 times heavier, natural period is so long, everything is wrong. And the mistake is wrong value of the unit weight. Things like that. Very simple and most common mistakes that you can make. Anyway, so if the natural period is too wrong, check your model. If your model is okay, that means structure is wrong. Fix the structure then, right? Check where is the problem, whether it has too much mass or too small stiffness, something like that. So in any case, the first thing is natural periods must be checked. Then you check the mode shapes. Like this one. So you should separate the boards. This is one of your buildings, right? Do you know which building is this? No? Knightsbridge. So you look at the modes, modal properties, response, and you separate the modes into these groups. Mode number 1, mode number 2, mode number 3. And then the next mode in the same direction, because there are 3 directions of the structure's movement, so each mode will repeat after 3. So X direction first, next mode in X direction will be number 4, next will be number 7, like that. Y direction, first mode, next one will be second mode, 5, and so on. So you separate them and draw this diagram every time, and I want to see all of you having this diagram in your report. If you don't have it, you will not get the marks. So plot your response, modal response in this manner. 9 modes of the buildings should be plotted with the shapes in each direction, and then we can see what's going on. And also plot what is the percentage of mass participation in that mode. What does that mean, mass participation? Why is mass important? Because it's modal analysis. Modal analysis means mass and stiffness. So that means mass and stiffness must be combined together. So theoretically speaking, if the structure is very small and single degree of freedom, in the first mode, all of the mass should be moving. If it is ideal single degree of freedom structure with a ball at the top of its rod, when you move in first mode, the ball or all the mass should be moving. So the modal participation is 100%, right? But in real building like this one, it cannot be, because some mass is moving, some is not moving in that mode, right? So that means in a real tall building, many modes will combine to give total 100% response, modal participation. So the total base shear, which is going to be sum of all the modes, will also be from many modes, not just first mode. Here we can see first mode is capturing about 60% of the mass in that direction. Second mode is capturing about 66% of the mass in the other direction. Remaining 40% is not participating here. This mode is getting 18%. This mode is getting 6.5%. So this must total 100. This must total 100. This must total 100 in each direction. And here you can detect whether the building has single mode response or higher mode response. So if 100% mass is here, about 90% mass is here, that means the building is a single mode response building. Single degree of freedom is okay, and equivalent static method can be used because that is based on first mode response, right? So from here we can see what method we can use. It is like, I mean, if I can continue the whole many days talking about modal response and how much information you can extract from this analysis. And then, like I said, it's a heartbeat. We can know everything about the structure by just looking at the modal response in the right way. Continue, I can honestly continue for many lectures only talking about modal response. So if you want to understand structures, understand modal response. Where it comes from, what it means, what to do, how to change it, how to control it, how to interpret it, so on and so forth. Anyway, so this one 60%, 18%, that means 78%, another 7%, that means 80 something percent. So that means still a few more modes are needed until you get about 90% response. So you must include enough modes in your analysis that every direction about 95% mass is participating, right? And then same case here, 66%, 50%, 5%. Torsion mode normally has no modal participation because torsion cancels each other. So torsion does not contribute to earthquake forces, and that is a very interesting thing, because if your primary mode is torsion, you will not get any earthquake force generated at the base, and you will think my structure is beautiful, I'm not getting any base shear, and you will be completely misled. But what is happening is all the forces are conducing, but the forces in the members are very large, even though there is no net base shear, because it's rotating about the center, right? So that is why torsion is very dangerous. People who do not understand that, they misunderstand, they think, oh, my building has very low base shear, but that doesn't mean anything. That means some members may still have very large forces, right? Okay, let's stop here.